I'm going to present a short case study about archaeological case study using some of the data science principles and methods to understand the Neolithic settlement patterns in the Carpathian Basin. So I'm going to talk about how I use the bulk of radiocarbon dates, get insight into the pattern of formation of patterns in the Carpathian Basin. So I'm going to introduce some techniques how to deal with a large amount of radiocarbon dates, new ways of thinking about radiocarbon dates, and I'm going also to introduce a new tool, not introduce, just present a new tool called R, the framework for scientific data science computing. So let's begin. So what we call Neolithic is a kind of shorthand for several historical processes on different time and spatial scales. So the processes behind the Neolithic are a result of formation and development of relatively stable and resilient assemblage of human material relationships, which develop in an increasingly structured, organized, and consistent social world. Yeah? But there's also kind of big picture story, a kind of historical drama, where we see a spread of new material assemblage from the southeast towards northwest over a span of several millennia, which resulted in a rigid thing that we call the Neolithic. So the aim of this paper or this presentation is to approach the process of Neolithic and Copper Age settlement patterns of a western part of the Danube watershed above the Danube-Sava confluence, based on the available radiocarbon dates. And this includes so this area marked here. So this includes Western Carpathian Basin, Eastern Alps, and eastern fringe of Dinaric Mountains. So development of radiocarbon dating, especially IMS dating, was kind of revolutionary event in the history of archaeology. It kind of started the second scientific revolution in archaeology. And with a large number of dates now, it is possible to access the past dynamics, not as a single big entity, but as a process kind of thing that can be sampled using radiocarbon dates. So radiocarbon dates are our main source of information, but dates are traditionally used to date the single events, contexts, sites. It's, of course, it's never just a date, just a number. It's a probability distribution, and it dates the end of the metabolism of a organic thing, plant, animal, stuff like that. But traditionally, it was used as a kind of data point for dating site, context, stuff like that. But with the development, with the large quantity of radiocarbon data, each individually dating a single local event, as I said, almost meaningless in itself, this transforms with a large number of dates, this transforms into a new quality, allowing us to approach larger spatial and temporal patterns through flux of local and singular events. So this kind of big data approach, not looking at the data points, but looking at the bulk of the data, allow us to approach the Neolithic as a set of local historical trajectories, each with its own spread, tempo, rhythm, and stuff like that. We can begin to see kind of series of regional and local responses and actions behind this larger process. So basically, what I did in this case study, I tried to treat the Neolithic as a kind of spatial temporal entity, which is sampled using radiocarbon dates. So, and the settlement proxies used in this study are based on what is called the temporal frequencies of radiocarbon dates, which are represented as a kind of sum probability densities. So the way to aggregate all these dates is just one of the simplest way to aggregate these dates is to sum them together into this summed probability distribution. And this sum probability, the underlying assumption of this sum probability density is that the number and the distribution of radiocarbon dates in time and space indicate the existence of settlement systems and settlement intensity, as more people and more settlements result in more activity and more radiocarbon dates. So basically, the shape of the summed probability distribution in time indicates, we assume that it indicates the intensity of occupation. Yeah, this is not without a serious problems, a number of serious problems. The whole approach, the whole idea, in a way, conflates the process variation, this variation in density, with chronological uncertainty. So you never know whether those peaks are the signal. Are they really a result of the settlement density, more sites, more people, or are they just the artifacts of the calibration curve, etc.? That's one problem. The other problem is that radiocarbon samples are not collected randomly. It's not a random sample. They are not collected randomly between and within sites, and this process can be heavily biased by sampling intensity and history of research. So some sites can be heavily sampled with radiocarbon dates. Some sites can be, you have 1 or 2 dates. Even some layers within sites can be oversampled because, you know, the researchers were interested in the maybe beginning of the site and stuff like that. So we are not dealing with a random sample. This bias can be to some degree offset by the aggregation of data. So we assume that sufficiently large regional sample of radiocarbon dates will counteract any problems at the site level. Yeah? And multiple small non-systematical samples from large number of sites constitute a quasi-random sample of regional trends and occupation. So basically, the idea is if we aggregate from a region, treat them together, it will in a way counteract the problems with sampling on a site level. Yeah? And this is also my idea. Yeah? In this case study, I aggregated the radiocarbon dates within the grid cells. So I divided the study area into the grid cells in 320 grid cells, I think, each covering around 520 square kilometers. And at this resolution, we assume that what's the archaeological archaeological idea behind this large grid cells or this aggregation. At this resolution, we assume that each grid cell represents the area of regional settlement system or settlement cluster. So a regional settlement system could be defined as a kind of interacting, interdependent groups of people. It contains several settlements and communities tied mainly with the exchange of various kinds into kind of regionally integrated social networks. So in a way, tribes, maybe level of tribes, something like that. So the procedure goes like this. The radiocarbon dates are first beamed into the grid cells, are collected within each grid cell, then sorted in a decreasing order within each cell phase, and then dates are calibrated, and then some, that's so basically, we treat the all radiocarbon dates from the grid cell, from different sites, as one set of data. This set of data is first beamed into the grid cell phases. So basically, this in a way counteracts oversampling of if you have some layers or some periods oversampled, usually the early Neolithic is usually oversampled. You have much more dates from the early Neolithic than from late Neolithic, for example, because people were interested in the beginning of the sites. So how you counteract this? You basically divide your period, your whole area period occupation into bins, and then aggregate dates within bins. So you calibrate them, and then you create SPD density plots for each bin, and then calibrate and then add them together. So the resulting SPD probability density of the whole cell is basically sum not of all dates, but of SPDs of each of the bin within the cell. So basically, we are using aggregation as a way to counteract the oversampling, the sampling problems within this region. So, for example, here is one of the grid cells in my study area. There are quite a lot of sites here. We have radiocarbon dates from these sites. I think there are 28, if I'm not wrong. They are individually calibrated. So we have the individual calibration curves for each of the dates. And then we add them together, but not just all together, but within the bins. So these bars at the bottom of my plot are individual bins. So basically, this is some probability distribution for the grid cell. It indicates, in a way, the pattern of intensity of settlement within the grid cell. So we can see that it started just before this 6,500 BP, and it ends, wherever it ends. Yeah. Okay. So we compiled a database of 141 sites with radiocarbon dates from the Neolithic to the Copper Age. The study area was divided into the grid cells. We collected around 820, but some of the dates were discarded because of the problems. So in the end, we used 750 dates in the study, and this is the main, let's say, data density for the study. Yeah. So one date for 4 years, 2.3 dates for grid cell, one date for cell in a 1,250 years. Quite a low data density, but that's the reality we are dealing with archaeology. We try to get an idea of the pattern from this low density. Yeah. So for processing part, we used an environment or tool for processing this data, which is called the R. So R is a framework, is programming language or framework for statistical computing, basically. A very, very powerful system or framework, which allows a lot of procedures for dealing with different kinds of data. But the main power of the R is that lies in its, let's call it, ecosystem of packages and libraries that can be used for statistical computing. So, for example, for processing radiocarbon dates, there is an R-carbon package developed by Enrico Crema and Andrew Bevan. Yeah? And I use this package for dealing and manipulating radiocarbon dates. Yeah? So basically, it's quite easy to, let's say, interpolate and calibrate 750 dates within the R. And those of you who are proficient, let's say, with Oxcal, 750 dates in Oxcal, it's quite difficult to do it. But in R, it's quite easy, if you know how to do it. So here are examples. But not only radiocarbon dates, it allows also the manipulation of spatial data with this powerful SP package, which basically converts R into the GIS. You can do everything you can do in GIS, you can do within the R environment. All kinds of managing, processing, and computing with the spatial data. So basically, you can load the GIS data, shape files, digital elevation models, and process them within these environments. And what is also one of the powerful packages within the R is the visualization. ggplot package allows many extremely powerful ways of visualizing your data. Yeah, there's quite a large community of archaeologists using R for different projects. Yeah? Here is one of the online books that you can look at about using R for archaeological science. And R is a programming language, so you basically have to type in your commands, you know, make a small programs, but there are also interfaces or programs or environments that make it quite easy to do this. And RStudio is one of these environments which allows you to, you know, approach R, which is quite difficult by itself, in a kind of more user-friendly, but still as a programming language. Yeah, and I'll show you now my program and how to do it. So basically, it looks like this. Yeah, you load libraries, you load data into it, and do all the processing as a kind of set of commands which execute in a line. So, for example, I won't go into details. I mean, I won't go into details here. Just as a kind of an example, we'll do the first plot I'm going to show in the presentation. And this is the density of radiocarbon dates per grid cell. Yeah? So just a kind of context, we have already imported the radiocarbon dates as the comma-separated values file. We have already imported the GIS data as the shape files. We have already created the grid using kind of regular sampling of the area, stuff like that. But now we are going to merge together the radiocarbon dates and grid cells. So in a way, we'll get information for each grid cell, how many radiocarbon dates are within the grid cell, and we are going to visualize this as a kind of map. Okay, and I will plot it using this ggplot. And the result should be something. That's how it works, basically. That's how it works. And that's also the next plot in my presentation. So as you can see here, the distribution of radiocarbon dates is, as expected, quite uneven. We have 320 grid cells, but only 77 grid cells are occupied. And this patchy distribution of occupied grid cells reflect the uneven density of the Neolithic sites, Neolithic settlement pattern, but also kind of different research strategies. So this cluster of sites, which extends from Balaton Lake towards Slovenia, yeah, this is results of the motorway projects in Slovenia. There's also a lot of bias within this data. So we have to treat it as a kind of remnant pattern of the actual distribution of sites. So yeah, we have some agglomeration into several contiguous clusters in Slavonia, for example, southeastern Alps, across western and central Danubia, and in the Vienna Basin. And there are some curious gaps as well, yeah, especially large one in the Alps, but also smaller ones elsewhere. Yes, that's the beginning. Yeah. So we have radiocarbon dates within the grid cells. We calculate the SPD of each grid cells, and then we can look at the lower when it starts, when the occupation starts, yeah? And we can plot this. This is basically the earliest date that the occupation starts. When the probability distribution is over some predetermined threshold, yeah? And it kind of shows the dates of earliest occupation, which clearly demonstrate that the earliest grid cells are concentrated in the southeastern edge of study area, mainly in Slavonia, around or soon after 8000 calibrated with P, but some isolated grid cells with very early dates are also spread all over the study area. So you have some around here in Western Transdanubia, around Vienna Basin, near the Budapest, some quite early dates. So it seems that within the first 500 years, after the first appearance of the Neolithic in Slavonia, Neolithic sites can be found all over the study area, except in the Alps, maybe. So the first Neolithic thus appears as a kind of isolated islands or enclaves of Neolithic settlements, which then slowly expand to fill the neighboring regions. However, there are some areas, especially southeastern Alps and area west of the Mura river, which are consistently settled much later than their neighbors, especially this part of Slovenia, the southeastern Alps. You can see you have much later dates than on the east. So basically you have kind of east-west pattern of dates. But this is, as I said, only a kind of remnant pattern of the real process. Yeah? So we approach the spatio-temporal pattern of this 2000 years old process using Kriging techniques, which is a kind of geostatistical method which estimates the values at locations that have not been sampled based on neighboring samples and autocorrelation patterns in the data. So basically, it's a kind of interpolation techniques with which we will try to fill the gray spaces between the grid cells. Yeah. So we use the earliest appearance of data in settled grid cells as a data. We use these data points to interpolate this continuous surface of the earliest appearance of the Neolithic in the study area. So basically, it's a kind of spatio-temporal map of when Neolithic appears in particular area. So it's a kind of interpolated surface with values for the earliest estimated date of Neolithic settlements. So again, we can see the pattern much more clearly. Yeah, the core area for the spread of Neolithic is that between Sava and Drava. From the origin in Slavonia, the Neolithic expands. It looks like in two prongs, one along the Danube and the other one along the Drava, Mura, and eastern foothills of the Alps. This expansion is in the form of several very early enclaves, such as those along the Danube, Vienna Basin, and western Transdanubia. Those enclaves are limited to one or two grid cells. What we see here is probably only surviving remnants of the string of communities that stretching around, along this expansion corridors. Yeah? And there are also some backwater areas, which much later Neolithic occupation. The most prominent being the area of the Alps and the smaller area south of the Balaton Lake. Some of them might be the result of the research bias, but definitely the Alps does not seem to be the artifact. The large number of dates from the southeastern Alps indicate the relatively late arrival of the Neolithic and then rapid expansion along the river valleys. So basically, this pattern that we can see makes sense in a way. And dense isochrones, those lines of first appearance of the Neolithic, where we have the very dense isochrones, especially the western border of the Vienna Basin, for example, in western Transdanubia, are the areas where the Neolithic expansion towards the west was halted for almost 500 years to 2,000 years, and indicates the presence of the kind of stationary border on the western edge of this first Neolithic expansion. So basically, we can see where the border, stationary border was located. But this map or this interpolated results also has some other information. The distance and shape between isochrones encode also the rhythm, tempo, and direction of the process, which we can see or visualize more clearly as a kind of vector field, with the size of each vector for each grid cells indicating the speed and direction of spread. So basically, what we did is some basic GIS stuff within R, where we calculated the slope of this surface that we have interpolated, and they also calculated the aspect, the direction of where it goes. So, and this is visualized as a vector field. So each vector points into the direction of expansion, and the size of the vector shows the speed of expansion. So you can see that some, corridors, expansion routes. But what is interesting that although the overall speed of the process seems to be quite rapid, as we saw in the first slide, as the distance between Slavonia and Vienna Basin was crossed in 200 years, basically. So we have appearance of Neolithic in Slavonia, and maybe 100, 200 years afterwards, we have site Brunn near Vienna, which is almost 500 kilometers away. It indicates the average speed of Neolithic expansion of almost 1.7 kilometer per year. Quite speedy expansion that we can detect within the appearance of first enclaves. But what we see here on this map is something different, namely the local speed of expansion. This is generally very low, few hundred meters per year. And these local speeds indicate a different process, not the spread of enclaves, but relatively slow expansion of settlement systems around the core regions and enclaves, slowly filling the landscape with Neolithic settlements. This map shows us the rapid expansion of enclaves all over the study area, but with this map, we can see the process of filling up the landscape, filling of the landscape with Neolithic settlements, which is much slower than this rapid expansion. Okay, so what else can we do with radiocarbon dates? We can use some probability densities as a kind of crude demographic estimation of the study area, and this is how the radiocarbon data is often used in this study. So basically you sum all the radiocarbon dates together, and from the shape of this SPD, you kind of estimate the demographic trends within the region. So as we can see, the rapid increase from 8,000 to 7,500 calibrated BP, with another push after 6,300 calibrated BP. And then there is a pronounced dip in the curve with small increase and a local peak just after 5,500 calibrated BP, following the slow decrease and the add-on time frame. But as I said, you never know with this graphs, SPDs, what is signal here and what is just noise or result of uncertainties in radiocarbon datation and calibration. So you never know whether this dips and peaks are just artifacts of the calibration curves or real indication of the demographic increase, stuff like that. To overcome this, you usually do some kind of elementary statistic analysis. So basically, you try to estimate whether this peaks and dips are statistically significant. And you do this by comparing your data, this empirical curve that you can see here, with some kind of model. Yeah. So basically, in this case, we took the stationary model, an idea that the level of occupation was stationary. You sample this model, you take dates from them, you calibrate them, and then you see the 95% probability that this calibrated model falls within this 95 probability. This is this shaded belt in the middle. So where your empirical model is significantly below or above this 95%, you can say that this dip or peak is significant. So in our case, we can see that this increase is this first violet part shows significantly low population, which is expected because of the it's in the area of the curve where the population raises. But this peak in the middle is statistically significant, and also this dip after 6,000, around 5,800, 5,700 BP is also statistically significant. Even more interesting are regional differences. How to access the regional differences. So, just as a kind of demonstration, I'll show you how to compare the area of the Eastern Alps, which is marked here with orange grid cells, with the rest of the study area. Yeah. So we compared empirical SPD curve for this whole study area with the SPD created for the subset of grid cells from this study area. And those are those. The idea was to evaluate the regional variation in settlement trends, possibly indicating some different processes behind the settlement of Southeastern Alps. Those are both curves that can be compared. The curve for the Southeastern Alps rises rapidly after 7,000 calibrated BP, but most of the growth is between 7,000 and 6,300 calibrated BP, and can be attributed to the expansion and growth into the Southeastern Alps. This is the curve of the statistical significance of the Southeastern Alps curve, and this peak is significant. And this is the Southeastern Alps compared to the whole study area. So this shaded area is the whole study area, and this green and violet parts of the Southeastern Alps indicate where Southeastern Alps curve statistically significant differs from the whole study area. So we can see that at the beginning, much slower race. This gap, settlement gap is statistically significant, but then afterwards it's also significantly more settled than the rest of the study area. So this spatial pattern of this process is clearly shown in a sequence of the settled grid cell maps at 500 years interval. So basically what we do is create a kind of animation of settled grid cells using this data. We can do it on a year scale, basically, but I'll show just 500 years sequence. So this is the situation at 7,500 calibrated BP. Yeah, it started as a kind of sparse, isolated grid cells in Slavonia, along the Danube, Bosnia, and the eastern edge of the Alps. So after the formation of this initial or core settlements, a gradual process of aggregation continues as a slow infill of the landscape around initial settlement. So basically what you can see around 7,000 calibrated BP is filling of the landscape with Neolithic settlements. But as you can see, the western part is still empty. Between 7,000 and 6,500 BP, we can observe a process of expansion into Alps, basically, into southeastern Alps, into Slovenia, but also along the Danube, deeper into the Alps. And then you can see the transition from the late Neolithic to the Copper Age is usually marked by the change from the nucleated to a dispersed settlement pattern. So in the whole Carpathian Basin, the previously not nucleated large delta sites were replaced by smaller flat settlements. And you can see this as a kind of abandonment of large sites. And this visibility also reflects in a spatial distribution. You can see that less occupied cells, visibly occupied cells. They were probably occupied but with small short-term settlements. And this process continues after 6,000 calibrated BC with continuous expansion into the marginal areas, especially Alps, and extensive abandonment of breed cells in the lower reaches of the Sava, Drava, and the Danube. This is the situation around 5,000 calibrated BP. So in this case study, we treated Neolithic as a kind of complex spatio-temporal phenomena, which we sampled using radiocarbon dates. So we took the radiocarbon data from the area as a kind of sample of this process, and we tried to see the pattern and the process within this data. So it's in a way a kind of big data approach to data. We are not concerned about the individual data points, trying to contextualize it, see if it fits in a model, but we take a bulk of the data, analyze it, and try to see if there are any patterns, meaningful patterns that we can interpret in an archaeological way.